Hello friends, now we will start with the class B amplifier with complementary push-pull arrangement. This is the circuit diagram of class B push-pull amplifier with complementary arrangement. Here we have two transistors NPN and PNP, both connecting in complementary arrangement. You can see during positive half cycle of the input voltage, this will be plus, right? When this is plus, this NPN transistor will be forward biased and the output will be, your input signal will be coming here. But see carefully, when you see the relationship between the input and output voltage, what is output voltage? Output voltage is input voltage minus VBE, which is approximately equal to Vin. So the output voltage will be approximately same as input voltage. So the gain of the amplifier when NPN transistor is on is unity, right? So output will be same as input when during the positive half cycle of the input voltage. Now in second half, when this is negative, this is positive, so this will be NPN will be reverse biased, this will be reverse biased, this will be forward biased. So during positive half cycle, NPN is forward biased, this junction is forward biased, so NPN transistor is on, this is off. During negative half cycle, this is on and this is off. Why? How this is on? Because when this is negative, this will be negative and supply voltage will come here, it will be positive and it will be on. So during negative half cycle, this is on. During positive half cycle, this is on. So during negative half cycle, negative voltage will be reaching through this. This is voltage drop of VEB. So during negative half cycle, V output will be nothing but input voltage, Vin, and of course this will be VBE. You can add up, but this is negative, right? So output voltage will be approximately same as Vin. Fine. So this is how we get the output voltage in both positive and negative half cycle approximately same as the input voltage. So output voltage will be approximately equal to same as input voltage in complementary push-pull arrangement. Therefore, the voltage gain of complementary push-pull arrangement is unity, right? So that is how this transistor, this particular arrangement works. Fine. Now, what was the purpose of this? You see carefully, we don't require transformer on output side, we don't require a transformer on input side, so size will be smaller, cost will be small, and of course that advantage we discussed earlier, there are no even harmonics in the output, right? And what was the advantage? Crossover distortion is eliminated by using this particular case. Why? Because in this case we will see how that crossover distortion is eliminated. Fine. But that is the advantage of complementary push-pull arrangement. Now we need to find the efficiency of the, that is conversion efficiency of the amplifier. And you know what is conversion efficiency? Conversion efficiency, so we will see conversion efficiency for this case. So for just small theoretical introduction to this, both transistors in complementary operation are connected in emitter follower configuration. So voltage gain of complementary operation is unity. In complementary operation, NPN transistor is on during positive half cycle and PNP transistor is on during negative half cycle. So there should be on. So this is on during negative half cycle of the input signal. So complementary operation is also known as push-pull operation. Then the DC power is drawn from positive VCC during positive half cycle and from negative VCC during negative half cycle. So output across load is available during the full cycle of input signal. Fine. Now let us talk about the collector efficiency. We know the Collector efficiency is also known as conversion efficiency. That is given by, conversion efficiency is given by, that is P AC output, PAC output divided by PDC input, right? That is PDC input. That is the conversion efficiency of the amplifier multiplied by 100. We know what is AC output power. The AC output power is Vm by into Im by 2. That is equal to, of course, you can write that this, that is Vm square upon 2 RL. What is Im? Im is nothing but Vm upon RL. You can see from the circuit. This is our peak of the output voltage is Vm, divided by resistance will be current coming from the transistors, right? So that is Im is Vm by RL. Now let us talk about DC output power, input power, right? In DC input power, we have to take two half cycles, because during positive half cycle power is coming from plus VCC, and during negative half cycle power is coming from minus VCC. How that happens? Please see it carefully. When this is on, power will be flowing from here to here, and when this is on, power will be flowing from here to here, this way. Current will be flowing this way, right? So during positive half cycle, power is flowing from plus VCC. So this is, I'll say plus. So that will be equal to plus VCC into the current. Current is how much? That DC current, IDC. And when we say DC, we will see that IDC, right? IDC. But what is IDC? The current drawn from this supply. Current drawn from current drawn from this. So during positive half cycle, current is coming from this, current is flowing from this. So that is positive half cycle, and value of the DC value of the positive half cycle is VCC multiplied by Im by pi. How? Because if you take from positive supply, we have the current only during the positive half cycle. This is the collector current coming from IQ1, and the DC value of this is what? Im by pi, if this value is Im, right? So if this is Im, that is how we have, right? So this is during negative half cycle, PIDC during negative half cycle is VCC into IDC, right? And both are negative. Why? Please see carefully. In this case, current is coming to the supply. In this case, current is going to the supply. So current is going here, it is going to the supply, and this is IDC. So when both are negative, because it is being taken, so power becomes positive. When current is negative, means when current enters into the supply is negative, when current leaves the supply is positive, right? So in this case, both are taken as negative. So this is minus VCC. Minus VCC into IDC. And remember, during negative half cycle, what do we have? This is minus, this is minus, this is minus. So the IDC is nothing but minus Im by pi. It was negative. And this is VCC I'm sorry. So this is VCC Im by pi. So total power taken from the DC source will be PIDC during positive half cycle plus PIDC during negative half cycle, and this is equal to VCC Im by pi into 2, because both are added here. So 2 VCC Im by pi. Now let us see the conversion efficiency. So the conversion efficiency here will be equal to, that is DC AC output power is Vm Im by 2 divided by DC input power is 2 VCC Im by pi multiplied by 100. And you can see this Im and Im gets cancelled out. So this is equal to Vm pi by 4 divided by VCC multiplied by 100. That is the expression of efficiency of class B push-pull amplifier with complementary arrangement. That is the expression of the conversion efficiency. I hope you can understand that. Right. Now, advantages of complementary arrangement. We have already discussed size and cost will be less. Humming noise is eliminated in this case. Why? Because there is no transformer. Transformer is the source of humming noise. So when there is no transformer, there is no humming noise. Then we have crossover distortion. So crossover distortion is eliminated by class B amplifier. Then disadvantages of complementary arrangement. What are the disadvantages? It is difficult to fabricate the transistors of matching characteristics. In this case, both needs to have matching characteristics for simultaneous for elimination of crossover distortion in the circuit. Then we have considerable distortion is introduced because even harmonics are not completely cancelled out in this case. So these are some of the points you need to remember. Now let's take the example. The circuit of class B push-pull amplifier is shown below. The output voltage is 16 volt, right? If output voltage is 16 volt and that is peak output voltage, power drawn from the DC source will be. Please see, in class B amplifier, what is efficiency? Efficiency is output DC power, output AC power by input DC power multiplied by 100, right? And that is equal to what? Vm pi by 4 by VCC into 100, that we have just seen. So in case of this arrangement, what is the efficiency? Efficiency is 78.5% maximum. So output power DC, that we have to find. Now please see carefully, peak value of the output is given. So what will be Im? Im will be peak value of the output voltage divided by 8. So that is 16 by 8, right? 16 by 8 means 2 ampere. 2 ampere is the peak value, and we know I have to find the power drawn from the DC source. So what is power drawn from the DC source? PIDC is equal to, we have already seen that, right? So the power drawn from the DC source is nothing but that is VCC into Im by pi from the positive supply, right? And total power, if you find, that is 2 VCC Im by pi, that is 2 multiplied by VCC is 25 volt, that is 25 into Im is 2 ampere divided by pi. You can find that is your total DC power, and that comes out to be, you can calculate that comes out to be 32 watt. That comes out to be 32 watts. So you don't need to go for efficiency and all. Reason because the question is not power, the question is on power, not on efficiency. So that comes out to be 32 watt, right? Now let us take another example. The input signal, you see the question, the input signal being shown in the figure is 1 kilohertz. So 1 kilohertz square wave. So the input signal here is 1 kilohertz square wave like this, right? That is input signal that alternates between +7 and -7. So this is +7 and -7. And remember, the complementary arrangement has unity voltage gain. So indirectly we can say we have a square wave at the output which varies from +7 volt to -7 volt. So output voltage is this, right? Both transistors have same current gain which is large. The circuit delivers power to the load RL, which what is the efficiency of the circuit for given input. So I have to find the efficiency, right? Now let us see the peak value. Peak value of the output voltage Vm is how much? That is 7 volt. Peak value of the output voltage is 7 volt, right? So now, what is peak value of the output current? Peak value of the output current is nothing but, that is Vm by RL, that is 7 volt by 10, that is 0.7 ampere, right? Now, what is the AC power drawn? The AC power drawn will be VPAC, output AC power, P naught AC power will be equal to VRMS square upon RL, right? This is what you have, but for, right? Now, we know for square wave, remember this thing, for square wave, what is there? The RMS value is same as peak value. This is what you have, you should remember this. For square wave, RMS value is same as peak value, so this is 7 volt. So output power AC will be 7 square by how much? 10, and that is 4.9 watt. That is output AC power. Similarly, DC input power will be what? PIDC will be what? That is VCC multiplied by the DC value of the current. And you know DC value of the current. DC value of the current is what? That is same as for a square wave. DC value is same as AC value, right? RMS I am talking about, but when you say DC, so the DC value will be same as AC value in this case. So for first half cycle, this will be there. For negative half cycle, this will be there. So PIDC will be equal to VCC multiplied by IDC, and that is equal to, if you take overall value, that is peak value, you can say, right? So that is VCC into IM. So that is, VCC is how much? VCC is 10 volt multiplied by how much is IM? That is 0.7 volt. So this is 7 watt. How did we calculate that? Please try to understand. During positive half cycle, this is on. When this is on, current will be flowing from this. So during positive half cycle, I'll just remove this. During positive half cycle, let us see that. I'll remove this also so that I can explain you. During positive half cycle, P output DC, during positive half cycle, P input DC is equal to VCC into IDC, right? That is during positive half cycle, and we know this is 10 volt plus IDC current coming from this side to this side. And during positive half cycle, what do we have? We have this, and so on. This is 7 volt. Remember, when it is square wave but only available for positive half cycle, that is equal to, this is peak value of the voltage, or if it was current, this is 7 by how much? This is the current, peak value of the current is 0.7 ampere, so this is 0.7 ampere. So this will be peak value of this divided by 2 when it is half, when it is flowing only for positive half cycle, so 0.7 by 2. And during negative half cycle, PIDC, during negative half cycle, that will be VCC IDC, and that is minus 10 volt multiplied by 0.7 by 2 during negative half cycle. Why? Because during negative half cycle only these currents will be available. Current will be available only for negative half cycle. So during negative half cycle, this will be the waveform, and this is 0.7 ampere, so divided by 2. So total IDC will be basically sum of these two. When you add up these two, this will be 10 into 0.7, and that is how much? 7 watt. So let us talk about efficiency. So I can remove this part. So efficiency is nothing but the ratio of, I have already written that, efficiency is ratio of, what is efficiency? Ratio of AC output power by DC input power multiplied by 100. You know what is AC output power? 4.9 volt. What is DC input power? 7 multiplied by 100, that many percent, and efficiency here comes out to be how much? 70%, right? So efficiency here comes out to be 70%, and the nearest value comes out to be this value.